Hello, my name is Austin. I'm going to be showing you how to do the XFLR5 Fundamentals of Aero project. First things first, we're going to start with the airfoil, which is a NACA 4412. We're going to go to Module. We're going to go to Wing Direct Foil Design. We're going to go to Foil, NACA Foils. We're going to do 4412. I'm going to click OK. Scroll this up. We're going to click OK. Now we have that 4412 NACA foil in there. Then we're going to go to module. We're going to go to XFoil direct analysis. We're going to go to analysis. We're going to go to batch analysis. Now I already have these put in here. It saves it from your previous runs, but essentially I'm doing 1.1 to 1.5 and 3.3 to 4.4 million for my Reynolds numbers. I already have the minimum alpha that Professor Osby wants of -5 and the maximum of 20 at an increment of 1. So that looks all good. We're going to click Analyze. It's going to go through all those Reynolds numbers, and it's going to output us some data. Perfect. These all look good. Look how they should. So now that we have that, it's time to do the plane. So we're going to go to Wing and Plane Design. We're going to do the different wings. We're going to plane, define a new plane. We're going to call the first one AR12 rectangular. That's not spell that. There we go. Rectangular. Unselect the elevator, unselect the fin, click define. We're going to set the Y. I've already done the math for these. 12, the chord, 2, the offset 0, the chord 2. We should have ourselves a pretty decent looking airfoil. Make sure you select your airfoil. That looks good. Perfect. And then we're going to do the same thing for the other 3. So the next one is a AR12 with a taper ratio of 0.3. So I'm going to call it that. Unselect the elevator, unselect the fin, define, set the foils. I got these numbers as well. 7.8, chord length of 0.6, offset of 0. We're going to have a chord length of 2. And we should have a good looking airfoil here. Yes, we do. Save, save, boom. Plane, define a new plane. Now we're going to do our AR6 rectangular. Perfect. Unselect elevator, unselect fin, define, select our airfoils. So this one is going to be 6, 2, 4. So we should have a rectangular airfoil here. Boom, we do. Looks good. We're going to save that. We're now going to go back to plane. We're going to define our last one. We have an AR6 and a TR, our taper ratio of 0.3. Unselect elevator, unselect fin, define, select your foils. So for this one, the chord length is 0.6 at a length of 3.9. Our offset is 0, chord length 2. So now we should have a decent, yep, there you go, tapered. We're going to save that. We're going to save that. And then we're going to define an analysis for each of these. My numbers are already saved, but I use these to get a Reynolds number of about 3.8 million, approximately 3.8. We're going to select all these. We're going to right click analysis, define analysis, make sure all the numbers are right, which they are. 30. Perfect. Define analysis, our data, boom, done. Okay. So now that that's done, now we have to run the analysis for each of these from -5 to 20 degrees alpha. Perfect. Analyzing pretty easily. The taper ratios of 0.3 have a harder time converging at those high angles of attack, but realistically, it's not that important at 20 degrees or 19 degrees. So let's go to our graphs. We have all the graphs that we should. These all look very good. So now the next thing we're going to do is we're actually going to show the local variations, which in the assignment we're supposed to do at 5 degrees angle of attack, the local lift coefficient, the local induced drag coefficient, the local induced angle of attack, and the local downwash velocity. So I'm going to show you guys how to do that. First thing we're going to do, we only want it at 5 degrees, so we're going to deselect them all and then reselect at 5 because we want to have only the 5 degrees showing because that's all that matters. 5 degrees, boom. So there's only the 5 degrees. Now we need to right click current graph, define graph settings. I think this might have frozen. It does like to freeze at this point. So we will see. It froze previously at this point. I don't know why this program does that. But let's see. Hopefully it recovers. It might crash on me, which would suck. It did. Okay, no problem. Okay, so unfortunately, I didn't save that one, which really sucks. So I'm going to pull up the exact same one. It's just got colors. It's the same thing. You can see it's all the same. I'm just showing the 5. Go back to here. I'll do the exact same thing. Okay. Right click, even though it's still showing. Deselect these. We'll do the same thing we were doing. I don't know why it decides to crash all the time. I'm not really sure why it's so crash happy, but this is the same file. You can see the lines are the same. I'm missing something. Yeah, there you go. You can see, and actually this will be easier for you guys to see. I'm going to zoom out a little bit. So we're going to right click. We're going to go to current graph. That's not what I meant to do. Current graph, define graph settings. Okay, so we have that. We want the x-axis to be the span because we want to see local. So at each distance. So the first thing we want is local lift coefficient. So we're going to click local lift coefficient. Perfect. And this graph does look good. We have our AR12 rectangular. We have our AR6 rectangular, our AR12 tapered, and our AR6 tapered. Makes sense. Then we're going to go to a current graph. We're going to go to define graph settings. The next one is the local induced drag coefficient. So we're going to click here. Again, very, very similar. It's pretty much the other graph just upside down. Then we're going to get the last one, the induced angle of attack. Again, looks pretty good, makes sense. Now for the local downwash, obviously they don't have a downwash setting. However, the formula for downwash is the induced angle of attack is equal to downwash velocity over free stream velocity. So if you multiply that free stream velocity over, you have downwash velocity is equal to the induced angle times the free stream. So if you take this graph and you multiply all the points on this graph by the free stream, which in this case is 30 meters per second, you're going to get the local downwash velocity over the span. Obviously, it's going to look like this graph, just shifted upwards or downwards, depending on your velocity. But with that, that is all of the graphs that we're supposed to do. This is all the data we're supposed to get out of XFLR5. Thank you for watching. Hopefully this was helpful in you doing your final project, or if you're just doing XFLR5 and you stumble across this video. Thank you.